Right, welcome to Verification Futures. We will start on time. We try to keep to time for anyone who's been before. I know we're quite strict about that, but yeah, very welcome. Just before we start, a big quick thank you to our sponsors, TestSolve, Cadence Synopsys, TechWorks, and UKS ESF, who are partners on this, AMD, Brecker, Siemens, and Nuri CDA. You'll be hearing from those speakers all through the day as well. And yeah, thank you for turning up. Thank you for being on time. Probably need to focus. Thank you. Not working. Okay. For overall, you've got 980 people globally. There's a lot of people online. Hopefully a few more people to turn up here as well. So that's why we do try to stay to time, because people will join online and go off online depending on who they want to listen to. But it represents 391 companies in 71 different countries. So we're growing, a good attendance, good registration. So this morning, you'll be hearing from Andy Bond, Brian Dickman, and Darren Galpin. And then a quick, the timing doesn't look quite right there, but Andy Penrose comes before Stuart Edmondson at night at 10:30, and Stuart's on at 11. Okay, and then refreshments and networking outside. And then we split into our different sessions, depending whether you're on formal verification, whether you're on the training session with Doulos or VHDL. And then we're back in here straight after lunch, and then we go back into some sessions. So it's all in your pack. So hopefully you know where you're going and when you're going there. And we will finish at 4:30. Okay. So just wanted to tell you about some of the things that we're doing. So TestSolve work quite closely with TechWorks. We've got the number of verification activities of the verification steering group, which meets probably about once, twice, 3 times a year to try and collaborate if we can on verification. And some training, design verification, and RISC-V. We're doing a lot of work at the moment on use of AI, ML in verification, if you're interested in that, and also verifying AI-based products. Okay, but I've done our thank yous, so I don't want to spend too much time. I just wanted to get onto our first speaker so we can get onto the real meat of the conference. And our first speaker is Andy Bond. I've known quite a while. It's good to have him as a keynote this year as well. He's been in the industry a while, so he definitely knows his stuff. He's now at Axelera AI, where he's the director of silicon verification. The title of his talk is "The Ghosts of Challenges Past, Present, and Future." He spent longer than anyone else cares to admit facing the increasing challenges of design and verification. As director of silicon verification for Axelera AI, he's embracing the world of AI after a career in audio, video, cellular, and financial industries. That as well. Let me just change your. Yep, that's the one.
Just check the mic before. Okay.
Yes, it's working.
Okay. Thanks very much. So, yeah, I'm Andy Bond. Title of the presentation: Ghosts of Challenges Past, Present, and Future. So, why is that the title? I mean, the simple answer is that Mike asked me to do this 6 months ago, and I needed to create a title that was generic enough that I could write it significantly later than that. So, can we focus?
Yes.
So, first of all, I'll do the thank yous first, because I might not remember to do it at the end. So, thanks very much to Mike. As he said, I've actually known Mike for over 20 years now. This event's been going for a long time, always gets bigger. It's a really good thing to do every year. So thanks very much to Mike and TestSolve for doing this. Also, thanks very much to Axelera AI for letting me do this. And more importantly, everyone I've actually worked with, all 4 over the last 25 years. As we all know, engineering is a team game, and everything I'm talking about here is because other people have told me what to say. So first of all, why should you care what I think? feel free to not. But 25 years of hands-on verification as an engineer, manager. These are some of the companies I work at. I started at ST in 2000, got spun out to SuperH. This is just two of the many, many logos we had at Icera before we got bought by NVIDIA. But it's been startups to multinational companies, including Cirrus, Logic, NVIDIA. I've worked by myself. I've worked in teams of 35 plus engineers, and I've done processor and SOC verification in most of those roles. And as Mike said, graphics, audio, cellular, fintech, and now AI. And 17 tape outs was my count when I added this up. And that's 17 proper tape outs, not metal spins or fixes or anything like that. That's 17 products. What I will do is to caveat this is, even when I worked at the big multinationals, I haven't been part of the cash cow product for anyone. So when I was at NVIDIA, I was not part of their GPU program. I was part of their CPU program. When I was at Cirrus, I wasn't necessarily working on the product for the company. No one's allowed to talk about. So it's always been smaller teams within large multinationals, but hopefully it makes it relevant. So first thing about what to expect from this presentation. So these are just personal opinions and philosophies based on my experiences. And very key to make, I'm not speaking on behalf of Axelera at this presentation. These are my views, not for Axelera. I know their logos on the bottom of all the slides, but that's because I was lazy and stole their slide deck. These are anecdotes that I probably should have checked before I put them down in this. And my opinions won't match everyone in the room. I know that lots of people work for different companies. Everyone's got their own flows. Everyone's got their own preferences. But hopefully some of them hit a sort of a general theme that people can accept. What not to expect is open season on the EDA companies. So I still have to sign licensing deals with all these companies, and thank you very much. Thank you for the generosity. So I think there's a bunch of you I've worked with in here. It's always been a back and forth, I think, on license negotiations and technology. So I'm going to try and keep that up. Also, don't expect comprehensive, well-researched experience. I have not investigated every possible offering of every possible company. I'm sure there are going to be some slide decks from people this afternoon that may address some of the things I'm going to talk about. And even more importantly, it's not a roadmap for anything successful. I can't tell you how to properly execute a project, and I can't tell you how to build a team. Every company is different. Everyone does it their own way. So first things all, and this is a slide deck I put in a lot of my presentations, verification is easy under three circumstances. Perfect specifications, so flawlessly defined by the architecture team, nothing gray, vague, anything else in that one, which I'm sure we're all very used to. Bugless implementation, again, designers never put bugs in. If they don't put a bug in, verification gets incredibly easy. You can predict how long things are going to take, and you don't have to worry about unpredicted changes late in the projects. And infinite time. So given we have all of those three for every project we do, it's surprising we hire so many people to do this. But the main theme of this is times have changed. So I started in 2000, as I said, with ST. So the left-hand side of this slide, for those of you who are students or were born after 2000, that's a Spark 10 processor, which is actually the exact computer I used when I joined, and that's a CRT monitor. It's a telephone, and that's Will Young, who was very famous in 2000 in the UK. And for those of you over 40, that's Taylor Swift on the right-hand side. And designs have changed. So again, I should say this is not a representative for anyone who I used to work for or working for. This is not a roadmap or a picture of their chips. But when I started, we were mostly doing CPU subsystems, which meant we had a CPU, we had some kind of bus, whether it was a ST bus or an ARM bus, and then we had a number of peripherals and a memory, and that was kind of the scope of the project we worked on. Then you handed that over to maybe another team who then wrapped it into a wider system, but it was a limited size, certainly one CPU generally executing one problem. It's not uncommon now to see something like we have on the right-hand side, where you've got multiple different types of CPUs, sometimes hundreds, if not thousands of CPUs on a chip, massive amounts of DSP or any kind of processing with colossal amounts of memory, with networking. Now that could be Ethernet, PCIe, USB, whatever it is. But it's not uncommon that this is now considered a project for one team to encounter. And going from my first project was on 190 nanometer to 5 nanometers, what we're doing now, colossal difference in the number of gates. and the amount of technology complexity. And the other thing to mention here is that workloads have changed. So this is just me stealing the PCIe numbers from Wikipedia to prove a point. So 2003, 32 gigabits per second. 2021, almost 2 orders of magnitude more at 1024 gigabits per second to a terabyte a second. It's a colossal difference in the amount of work that we're supposed to be looking into. But this is the more important part of this presentation is really that verification has changed, or at least in my opinion, it's changed. So again, I actually stole these two sentences from Mike from about 20 years ago. Validation is, have we built the right thing? Verification was always, have we built the thing right? Have we confirmed that the specification matches the implementation? But I don't think this is true anymore. And what I'm seeing is that systems of, I should always say, systems have always been complex. So anyone who hadn't seen a Spark 10 before and is amazed that we managed to design anything in 2000 to 2005 on that kind of level of processing, they were always complicated, but we always had to find a way to do it. But certainly over the last 10 years, at least, technology in terms of the amount of compute, the amount of memory, I mean, you can now buy boxes with terabytes of RAM, gigabytes of RAM, terabytes of memory, and farms and cloud computing that we couldn't even dream of 10 years ago. And the kind of chips we're designing have moved faster and further than we could have predicted at that point, in my opinion. But it does mean that requirements that we used to get, when we used to get a very defined expectation of what the chip or the project or the process was meant to do, isn't really true anymore. We now get an expectation of what the project's supposed to be, and we're supposed to fill in the blank with architectural exploration. And a lot of what verification is doing now is figuring out the performance, the interaction between multiple complicated blocks, rather than proving that the architecture was correct in the first place. So I think we're now verifying expectations rather than specifications. And this is kind of a crux of it. So I think there was an inflection point. I know a few of these guys are here today. So in 2000, there was really a sort of inflection point for logical verification. And it was mostly because the production costs and the competitive markets really put a focus on right first time silicon, and chips were getting bigger and more complicated. There was a big push for verification into the market at that point. And to be fair, Vericity, I know some of the guys are here, will really change the landscape at this point. ERM and Speckman, for those of you who don't remember it, was a big change. They were the first guys to really introduce coverage, randomization, almost verification planning, and reuse. And we moved from that design-centric mode where you could understand the entire project, the entire design in one person's head, to metric-driven, where we added in coverage, formal verification, and test planning. That was now 20 years ago. And to me, late 2020s, I don't think we're quite there yet, feels like another inflection point in what we have to do as verification engineers. So, and the reason for this is there's more forms of resource available. So we do now have cloud computing. There's a colossal amount of open source tooling and ecosystems available now. University projects all around the world are doing lots of more hardware verification. And it's also got lower cost. Simulation licenses have come down significantly compared to the overall cost of a project. FPGAs are now more widely available, both small and large. And with emulation as a service, I don't know if anyone had an emulator in the early 2000s, which was the size of a washing machine, made an absolute racket, and needed a power supply put into your office. You can now send it to the big three. They have farms of this, and anyone can now take emulation at a relatively low cost for the average. Also, the way we work has changed. Obviously, everyone knows COVID massively made a difference a few years ago. It's changed the way we work. It's a lot more remote work. We can grow teams across the entire world. We don't have to be centrally located. And that's changed the team dynamics. And also graduate expectations have changed now. So not only in terms of the reward structure, but the way they want to work, the types of projects they want to work on. There's more of a rush to accelerate your career prospects if you're a graduate these days, I think, than a long time ago. Also, there's a whole lot of new market sectors, and they have different revenue structures to some of the big semiconductor companies that we used to have. So yes, you've still got your Broadcoms, you've still got your STs, you've still got your Intels, but fintech has a very different profit model to semiconductor companies. They're not selling products, they're making money from the products they design. Automotive is changing from that design a chip 45 years later, it's in a car that you can actually make some money off if your company still exists and hasn't been bought by Bosch or someone else. Space race, again, billionaires investing a colossal amount of money into avant-garde projects. Security, and I'll say audio and video. And what I mean here is that people are willing to pay $10,000 for a sound system. They're willing to pay $200 for a chip that might only have 100,000 chips sold globally. The other part, which has really changed since I actually wrote these slides 6 months ago now, is, I mean, anyone who's looked at the stock market recently, there's a lot of investment into semiconductor and technology stocks because it's the only thing realistically that's making money in the stock market. So there's a colossal amount of investment going into technology companies. And then I sort of briefly announced it, artificial intelligence and machine learning. I'm sure there's going to be many presentations today because that's really cool stuff that people want to talk about. So this is my view of what used to be true. In the past, so this is system verification, so I'm talking about SoC, NOx, anything that's not a processor, basically. We used event-based simulators, your Incisives, VCS, QuestaSims, did a lot of waveform debug, so waveforms got progressively better. We had a lot of direct test cases and transactors 20 years ago. We looked at code coverage, expression, code line, and we used test cases to use for feature mapping and reviews. This is before things like verification manager, the equivalents for Synopsys and everything else came in. And now everyone's using a bit of a mix. So often now people are still using those same event-based simulators. Obviously, they got a lot better, but people use fast models from CPU vendors. They use Verilator, emulation, FPGA, all very common, even for the smallest companies now to have access to FPGAs and emulation. There's assisted waveform debug, which X-tracing, the sort of jumping to the interesting parts. So evolution of the waveforms has definitely happened. Probably the biggest thing here is that hardware software co-verification is really now a thing. People are debugging the hardware, the software, not just the firmware, sometimes the actual full end-to-end production software and hardware being reviewed. And that's led to a mix of direct test cases, constrained random. Incidentally, I kind of hate the word constrained random. I know this is industry standard. It kind of implies that random is the important part of that. I tend to go for scenario-driven testing because if you're testing anything difficult, you need to get from A to B. You can randomize around that route, but if you just try and do random stuff, you waste a lot of time doing debugging rubbish, in my opinion. There's a lot of reusable VIP. And again, formal verification is very common. Again, even small companies can use formal verification, whether it's in the app space that the vendors are now supplying, or full proofs. And really, we now discuss metric-driven verification as if it's a sort of a given that that's the way you sign off chips. You hit your coverage, functional coverage, code coverage, assertion coverage, everything else. So now we get to the bit UVM. Everyone knew this was going to be talked about at some point today. So this will be a brief history of UVM for those who don't remember it. So 99, 2000, ERM came out from Speckman. And then between, say, 2005 and 2011, there was OVM, VMM, multiple others. And it all kind of got merged together in UVM 1.0, which came out in 2011. I did look that up. It is the correct date. And the great thing about this is finally, as an industry, we had a common set of terminology. Before this, if you changed roles or you talked to other people in the industry, every company had their own way of describing a test bench. We didn't agree what a scoreboard was. We didn't agree what a test plan was. But now the concept of sequences, drivers, monitors, agents all became defined. Now everyone knows what they're talking about. We can discuss this. It makes it much easier to hire people, makes it much easier to get contractors in, makes it much easier to sell tools and VIP. So generally, this is the big, for me, this is the big win of UVM, was the fact that we actually had a common platform to discuss. Other sides to it, and this was very big at the time, it's an open specification and reference implementation. So it's the foundation for everything to come in the future. And it was in a language that RTL designers read. And this was, again, a really big thing at the time. Speckman, not going to knock it, very good language, introduced a lot of the things. Designers hated Speckman. It was a language that they couldn't understand. They didn't get aspect-oriented design. They didn't want to learn a second language and a second methodology on top of Verilog. So when this all got absorbed into System Verilog, it became a natural thing to move over. Not a criticism of VRM. I know a lot of companies still use it, but it made the whole team more effective by switching over to System Verilog. And then multiple updates of UVM, so it's been updated. The last release was actually 2020 3.0, released in February 24, so it's been supported. But that's not true. Did anyone actually even, show of hands in the room, did anyone even know there was a 2020 release of UVM? Anyone who wasn't involved in the release actually know there was three people. So I actually looked it up. There have been multiple releases. I don't know anyone that's not using 1.1D that happens to be installed with all the simulators. I don't think anyone even uses 2. No hands. So in reality, it's not open. It's not in development. It's been locked into EDA since it was created. The big 3 have pretty much dominated UVM. And actually, the big problem was the wide-scale adoption was the problem. There was a big boom. Lots of people adopted it very quickly, and it instantly killed any development because there were too many companies invested in the source code that they didn't want to update on projects. They all had deadlines to hit. And that's why we've been stuck on 1.1D since it worked, because it's very hard to update to a newer version. And there is really limited support outside the big 3, generally because of licensing reasons. Open source do not look at UVM particularly. The other thing I didn't really want to put on a slide, but is true, is that a lot of outsourcing and a lot of contracting companies got very big into UVM. And in my opinion, again, they focused way too hard on the details and not the purpose of UVM. A lot of the VIP is not of super high quality, and particularly the VIP addresses the how and not the why. And what I mean by this is, if I'm buying in VIP, I want that VIP to save me time and effort. Time and effort for me is not writing a BFM, it's not writing a sequence, it's understanding what the problem is and writing the test plan and the coverage and everything else that actually satisfies that test plan. If you don't provide me the test plan and what you're actually resolving, I spend all my time doing that. You've done the fun part, which is writing drivers and sequences and all the cool stuff that actually people like coding, but you haven't taken the risk off my shoulders. And that's very common in VIP, particularly unless you spend a lot of money on things like USB, PCIe, Ethernet, where it's a very complicated standard. And the VIP often just tells you how to wiggle the pins, not how to verify the block. So you've got one of the alternatives, and I put the big one down here. I know there are others. CocoTB. This is getting a lot of traction now. I noticed that Cadence are now officially sponsoring CocoTB. It's a Python, for anyone who doesn't know, it's a Python-based simulation test bench language. It's really strong on language. If you haven't written a test bench in Python, it's really nice. It means you can do a lot of the cool stuff of interacting with your Linux other libraries really easily. It allows you to write test benches really quickly. But it is weak on methodology. It doesn't really have any methodology built into it. And really, there is no VIP or quality common code. You can go out. There are university projects that have developed VIP and everything else in CocoTB, and they look like university projects that have implemented stuff in CocoTB. So what do I think the future is? Again, buzzwords that will mean nothing to you. I think the future is hybrid multi-threaded simulators. I think the simulator is a bit of a dinosaur that needs to be addressed. You look at the rise of Verilator, particularly in the world of processor verification, which comes in a bit. Verilator, you can get 3 megahertz out of a standard C-based Verilator model, compared to maybe 100 kilohertz if you're lucky out of a standard event-based simulator. It's a massive difference. If you're developing something that's predictable like a processor, the sheer productivity win of a non-event-based semi-accurate simulator is a colossal win. Hybrid emulators, I'll get onto that. I've got a couple of slides about it coming up. And then the big things I think in terms of the methodology we're missing is I see a big drive towards performance-driven verification, not metric-driven verification, and moving metric-driven verification towards requirement-driven verification. And as a big thing here is AI-assisted debug. As we've got more compute power and more tools and availability to us to do this, I think the AI-assisted debug could be the thing that drives this. The other part of this that is going to be coming up, and I know that Joe and Brian are presenting this next, is we are now able to generate vast amounts more data than we could generate before. We can run infinitely more simulations with cloud and licensing. We can generate longer tests on bigger designs that produce a colossal amount more design. We also are linked into things like GitLab, and we're linked into bug databases. How we actually efficiently debug that. I actually gave a presentation here about 5-6 years ago about big data and how understanding the data you're collecting was going to be a big problem. And I think that's coming up in the future. So what do I mean by hybrid simulation? So as I showed before, designs are increasingly macro or tiled based. So again, I'm going to get crucified for this when it goes out, but in my opinion, design has not moved on a colossal amount in the last 20 years. We have gained increased performance and increased compute by going through scale, and that means that we're now putting several hundred, if not thousands, of CPUs on the chip as opposed to one. And then we're using software and getting the flexibility of that programming through the scale increases. The actual processors themselves, again, slightly controversial, but if you look at a RISC-V processor, most of the ones you're buying now have the same feature sets as the SH4s, the ARMs we were doing in 2000, 2001. The processor itself has not massively improved. It's now open source and it's got scale and flexibility, but the actual complexity hasn't changed, of course. There are exceptions to that, which I'll get into in a minute. And then often the interactions between these processors or these sub-blocks is limited or asynchronous. And we know this because actually we've been doing this in verification for a long time now. We've been doing IP level test benches where we use a transactor to model the AXI port or the APB port, and we randomize the delays on those ports. That shows that we do not need to be cycle accurate on those interfaces, and yet when we run big sims, we're still doing that. And this is where we're sacrificing the performance of the simulation or the emulation by making it cycle accurate or event-based. I believe we can trade off fast cloud-based, allowed to trade off the accuracy to enable fast or cloud-based or supersized simulation platforms. And in my mind, what I'm seeing here is if you've got a chip with 1,000 CPUs, you should be able to simulate that on 100 Intel boxes or AMD boxes and run at megahertz, not kilohertz. On the emulator, again, we don't auto harden, so you can get fast models. So ARM provide fast models, companies provide fast models. But in general, if you're designing these large macro-based things, I believe personally that you could take out the replicator stuff, put it onto a lower cost platform like FPGAs, and then use the emulator for the flexibility stuff, which you're actually trying to verify. And this, I believe, is possible mostly because FPGA process and flow and design is actually quite tricky, but only if you're trying to hit very high frequencies. If you're only trying to match the frequency of the emulator, you've got a lot easier problem of mapping stuff onto FPGAs. Also, I put this on just because it's a personal grime. Smart NOC, analog and CPU models. Can somebody please write a PLL model or a memory model that's actually useful? I don't need all the timing parameters to be run in real time. It's a memory, it's a PLL, just give me a clock. Performance-driven verification. And this is a big one for me. I've been mentioning this to Cadence and Siemens and Synopsys for a few years now. I don't think we have a clear definition of what performance actually means. It's a complicated problem. We can say latency, throughput, but latency and throughput mean different things in different circumstances to different people. And the way you define this is often context specific. Also on this, metrics aren't discrete. We're very used to coverage points where we have a bin where it's been hit or it's not been hit. Actually, performance is probably a Gaussian where you have a mean latency and you then have a tail with a standard deviation. And you care about the tail and you care about the mean. It's not the same thing. And normally you see architectural expectation is difficult to measure. So you quite often get coverage or performance points where you say the memory has a latency of 3 cycles. And so you'll write an assertion that says the memory latency is 3 cycles. But then there's contention because someone else comes at the same time and they go, oh, well, it bank clashed. So it's actually 4 cycles in that case. So you change your test to 4 cycles. And they say, oh, when you run another test, it bank clashes for 2 cycles in a row and you actually get a latency of 5 cycles. And you end up not really verifying performance because you haven't defined the scenario where that performance metric is valid to constrain the performance you're looking for. And really why I put it on here is I think as an industry, and this is on the EDA companies, on everyone in the room, we haven't agreed a language to define the problem of performance verification. Now, I know some companies are working on this at the moment, but until we get to that point where, like UVM, we have a defined way of describing performance, we won't get anywhere. What do I mean by requirement-driven verification and AI-assisted? Context-aware debug. There are already tools to do this, but it's going to get better. What is unique about the failure that you hadn't tested in the other test cases that allow you to debug it and jump to the conclusion initially? Requirement-aware debug. So rather than just maybe looking at the assertions or the sequences, if we worked in terms of requirements, then we could maybe auto-correct bad sequences or fix bad checks. And we could use static verification code analysis to look at this. So quite often you get stuck in infinite loops. You have divergent sequences where actually the test case doesn't actually do what you want. Quite often we're good at detecting directly conflicting constraints, but where actually your constraint has accidentally over-constrained but not illegally constrained your stimulus is very hard to pick up. And you only get that later in the project where you have the metrics to bring in. I believe all this with AI and some of the formal improvements could be built in much easier. And when I say automatic requirement coverage, I think we should move to a level of abstraction. At the moment, we spend a lot of time writing assertions and properties. We spend a lot of time writing coverage. With AI now, I believe you could work on the requirements and get the AI to generate the metrics and the constraints for you to do this. I actually did this on ChatGPT yesterday in order to prepare for this. Sent ChatGPT. I've got an AXI interface, and it's the constraint is that the accesses have to be memory aligned, and it generated me 50, 60 properties that matched the AXI standard, and it matched the requirement I want. I didn't have time to go through them and check they were all correct, but it did it quicker than I could type it, and it did that. So process verification. I'll go through this very quickly because I'm running out of time. In the past, we were isolated to a small handful of companies. We only call they were Intel, AMD, ARM. I used a whole bunch of directed and constrained random test cases. Now, present, a lot of people have gone for a wider adoption of CPU, particularly RISC-V. A lot of companies have moved from having their DSPs or their state machine-based control paths, replacing them with a RISC-V for flexibility, software upgrades, and everything else. And we've moved from going from a transaction-style-based debug to a trace-based debug. So in the future, I believe that the fallacy of optimization is going to change on this one. And we're going to use that to drive the system being the focus of the products in the future. So what do I mean by fallacy of optimization? RISC-V open source ISA enables infinite possibilities, but it's actually the compilers, the timescale, and the resource that limit your ability to do this. What you're actually looking for is the flexibility of the software as the win in the product. Often the customization and optimization don't actually add the cost benefit. So my belief is that in the future, IP vendors will realize that the verification is the value add. Again, as I talked about, de-risking the project, not doing the cool stuff that actually your team want to do themselves. It's actually pretty easy to implement a RISC-V instruction set simulator. Implementing and verifying a fully pipelined model is much, much more different. And for this reason, I think high performance processors will remain high value, low choice IP from the big companies. What about formal? This kind of wraps up into the whole thing. Adopting formal was hard. It was very difficult. It was a steep learning curve. The industry is beginning to converge on best practices. Bug hunting, applications, designer friendly, foolproof is very rare. But I think that in the future, again, like simulators, we'll go to a more hybrid model by using a mixture of AI, formal, and dynamic simulation in order to do this. And that's where we need to wrap it all together to make this into an easy to use process. So conclusions, last 15 years have seen a massive progress in silicon technologies, product and scale. Let's face it, the industry as a whole has done a really good job. You look at the phones on those two slides, the difference in processing that we have between an iPhone and a Nokia from 20 years ago is ridiculous. Verification has kept up through taking advantage of hardware performance improvements, servers, grid systems, emulators, FPGAs. But more importantly, we've kept up through hiring. We've hired a crap ton of people in the last 20 years, and teams have got significantly bigger because of it. in my opinion, mainstream approaches have evolved from the 2000s view of circuit design. That doesn't hold anymore. We're still sticking to the principles of how we did verification 20 years ago, and we've got to let go of those and replace them with newer, better principles. We need to start trading off accuracy versus performance, accuracy versus reliability, and debug time versus development time in order to meet that. But we will find a way to do it. That's it. There we go.
Yeah, so save them for the break. A couple of things Andy touched on was Cocoa TB. We do have a DV club later in the year on Cocoa TB. Big data, and that's our next topic. So it feeds in nicely to our next topic. It touched on automotive, which is our third speaker, Darren Galpin, and the use of AI, which is our fourth speaker this morning. So it's a very good lead, and thank you very much, Andy. As if you read the agenda in advance.